If you strip away the sleek interfaces of a modern computer, you are left with a vast, volatile ocean of raw binary data. The machine itself is a pedantic beast. It has no capacity for nuance or intuition. It only processes basic electrical states, switching transistors on and off at high frequencies, fires an artificial language that translates our human intent into machine action. But to master JavaScript, memorizing syntax is only a partial solution. You have to build a precise mental model of how the engine physically allocates data and manages state under the hood. A novice often guesses at code structures until the errors disappear. An engineer understands the underlying mechanics well enough to predict exactly how the machine will react. This mechanical layer is where the computer transitions from a physical object into a programmable tool. To work with massive quantities of bits without getting lost, the JavaScript engine isolates specific chunks of memory and assigns them roles. These chunks are called values. Take the number type. JavaScript uses 64 binary digits to store a numeric value, reading the sequence to represent numbers like 13. Text requires a different structure, grouping 16 bits per element to represent Unicode characters, forming the string type. JavaScript is notoriously liberal in what it allows. Instead of halting with an error when different types clash, the engine tries to find a way to make the operation move forward. When an operator is applied to a value it doesn't expect, the engine quietly converts that value into a format it can use. This is called type coercion. If you write an equation multiplying 8 by null, the engine doesn't stop. It converts the null value into a 0 and completes the math to return 0. Some values refuse to map to a number logically, like multiplying the string 5 by 2. This impossible calculation produces NaN, or not a number. NaN denotes a nonsensical computation and carries a unique property: it isn't equal to itself. Understanding type coercion is critical because the system often interprets your input in ways you may not have intended. Once values are generated in memory, we need a way to combine and manipulate them. Any fragment of code that produces a value is called an expression. You can think of an expression like a sentence fragment. It contains meaning, but doesn't necessarily perform a task. Writing out 100 plus 4 multiplied by 11 creates an expression that evaluates to a single numeric value. To actually do something with these values, we use statements. If expressions are sentence fragments, statements are complete sentences that stand on their own. A statement affects the world, changing the machine's state or displaying on a screen, known as a side effect. Using console.log takes a calculated value and outputs it to the console, creating an observable side effect. Expressions manage the internal logic, while statements generate the observable side effects that let the program interact with the world outside its memory. When an expression generates a new value, that value is fleeting. Unless the program is specifically instructed to hold on to it, the bits dissipate. A common misconception is that variables act like physical boxes where data is dropped inside and stored. JavaScript manages state through bindings. We create these connections using keywords like let or const. Bindings do not contain values, they grasp them, like tentacles. Writing let Luigi's debt equals 140 creates a binding named Luigi's debt that reaches out and grips the number 140 in memory. These connections aren't permanent. The equals operator can redirect a binding to a new value. If a payment is made, the binding disconnects from its original value and instantly grasps the new total of 105. A program can only access values it is actively holding. Any data no longer grasped by a tentacle will eventually dissipate back into the sea of bits. Internalizing this model is essential for tracking how a program's state changes over time, preventing bugs related to data being overwritten or lost. Statements naturally execute in a sequence from top to bottom. We can branch this path using conditional execution. An if statement forces the engine to evaluate a Boolean expression, choosing one path while skipping the other. But programs often need to perform tasks multiple times. Looping control flow allows the engine to go back to a previous point and repeat it. To prevent a loop from running forever, we use a state binding as a counter. The while loop checks this counter before every repetition to decide if the work is finished. The condition is tested, the code runs, and the counter updates on each rotation until the goal is met. Control flow turns a simple calculator into an automated system capable of making decisions and managing complex tasks. When we combine values, coercion, statements, bindings, and control flow, we assemble a functioning mechanical system in memory. We can see this system in motion by computing 2 to the 10th power using a for loop. The loop starts with initialization. 2 bindings are established. One tentacle holds our starting result of 1, while another grasps a counter starting at 0. The engine enters the loop, multiplies the result by 2, and advances the counter, before circling back to check the condition. A processor cycles through updates billions of times per second, rapidly detaching and re-grasping 64-bit data chunks as the loop completes 10 iterations. On the final pass, the counter hits 10 and the condition evaluates to false. The execution path breaks out of the cycle, leaving our result binding attached to the final number, 1024. A program is an immaterial machine, a complex structure built entirely of thought. By internalizing how the engine handles state and memory, the behavior of a program stops feeling like an accident of syntax and begins to reflect the designer's intent.